Alright, hello everybody. Welcome to my walkthrough of Project 3 for the Fundamentals of Aerodynamics with Professor Osby. Um, for this project, we're going to be once again working on a flat plate, 2D flat plate with a combined flow. As you can see, some flow conditions here, 2D, viscous, steady, laminar. Um, a couple of important things here with our velocities at certain points along our flat plate, and some things for geometries here. So without further ado, we'll go ahead and open up Ansys. What we're going to want to do is go to Fluid Flow, Fluent, and you should get something like this. We'll go ahead and click on our geometry, change that over to 2D, and then you can go ahead and right click and go to New Design Modeler. That should just take a second, but here we're going to be making our flat plate, which is just basically a rectangle with our length and height. Um, for this project, we have a little bit more leeway in choosing our height and length, but you don't want to make it too high, or it'd be hard to see the boundary layer here, which it says in our project description, and it also tells us that our length has to be 150 times our height. So it should be loaded up here. So we'll go ahead and click on unit and change that over to millimeters. We'll go and get into the XY plane by clicking on this little Z down here, and we'll go to sketch. And then we'll go ahead and click rectangle. Like I said, we're just making a flat plate, so it's just a rectangular surface. So go ahead and make our rectangle. Go ahead and go down here to dimensions, general, and just click right here, and right here will work. For our height, like I said, we're able to choose. You just don't want it to be too high. I'm going to go ahead and set it to 3 millimeters, which then makes our length 450 because it's 150 times the height. You should get something that looks similar to this, depending on what height you choose. It should just be a very long rectangle. Now to make this a complete solid surface, we're going to go up here to Concepts, Surfaces from Sketch. We can click this little plus right here to select our entire sketch and click Apply. And then you should be able to hit Generate. And there you go. So you should have a nice smooth flat surface here for our flat plane. So then we're going to go ahead and go back over to here. Just click Update just to make sure it updated correctly. And then you can close out the Design Modeler. Okay. And then once that closes down, we'll go ahead and begin working on our mesh. Should just be a second. Okay. Yep. And then you can go ahead and double click here to open up the mesh. Yeah, it should just take a second. So like I said, for this project, it's a combined flow, so you're going to be working for our first part is to show velocity contours with vectors focusing on the boundary layer. And then obviously pressure contours, some velocity profiles, a couple of other things. So go ahead and see if that wants to open up for us here. Okay, it should be importing our flat plate that we just modeled a second ago into the window here. Yep, there you go. And just let it sit for a second so it can load properly. And then we will get started on working on our mesh. Okay, so there it goes. All right, so you can go ahead and right click on the mesh here, click Insert. Our first mesh that we're going to do is Method. For a geometry, you can select the entire flat plate, and then down here in Geometry, you can just click Apply. And that should do it for that one. Next, we're going to make some sizing meshes, so you can go to Insert, click on Sizing, and you want to make sure that up here you select Edges, so that we can select our edges here. You can go ahead and zoom in over here So we want to select the inlet. We can zoom back out, zoom over here, hit Control, and get our outlet. And click Apply. So you should have 2 edges for the geometry. For the type, we're going to change that to number divisions. We're going to make it 100. For capture curvature, we don't want that, so we can go ahead and click No. And for behavior, we can go ahead and select hard. Okay, and that should do it for that one. Then we can go to sizing once again. Make sure you have edges still selected. Click the top and bottom wall. Click Apply on Geometry. You should get 2 edges. And then once again, going through the same motions, we want number of divisions. We're going to change this value to 1,000. Curvature, no, and behavior, hard. And then for our final mesh, we can go to Insert, Face Meshing, and select the entire face. Go ahead and click Apply, and then we can hit Generate to generate all of our mesh. Okay, and it should have. Alright, so yeah, you can go ahead and check. By clicking on mesh, you should get a long flat plate that's completely black. But when you zoom in, yep, like that, you can see our divisions here and our mesh. So that's exactly what we want it to look like. And then lastly, really quick, to help us out later on, go ahead and select edge. We're going to zoom in over here. We're just going to select, select our inlet edge there. Click N on the keyboard and just write inlet just to label these. Click the top one, we'll label that upper for our upper wall. Click the bottom, once again hit N, we'll label that lower for our lower wall. And then we'll zoom all the way back out and zoom in over here and select our outlet and label that outlet for our outlet. And to check, you should be able to click here and see, you should be able to see we have inlet, upper, lower, and outlet. And that's exactly what we want. Okay, so then we can go back over here and click Update to make sure our mesh gets fully updated. And you can see it's successfully transferred. Okay, and we can go ahead and close out a mesh and get working on our simulation and contours. Like I said, for the first one, yep, go ahead and close that down. You can double click on setup here. A little window should pop up. Yep. We want that in 2D because we're using 2D model, double precision, and we're going to change the solver processes to 2. And we can go ahead and start that. While that's starting up, I'll go ahead and talk about what we're going to be doing. So like I said earlier, we want our velocity contours with vectors and focusing on the boundary layer. We want to show our pressure contours. We want to show the velocity profile at the mid and end section of the pipe on the same graph. And then we want maximum velocity and height at which the maximum velocity occurs, and then pressure gradient with theory. So that'll be our task here in a moment once it is fully loaded. Okay, you can see our plate is in there. It should be just about done. Go ahead and click OK on that. Alright, so we are all set to go here. First and foremost, we're going to do a little bit of housekeeping. So you can go ahead and click on Models. We're going to change this viscid, so double click on here to laminar since we're working with laminar flow. For our materials, we want to be in fluid, and since we're able to choose our own fluid with a Reynolds number, I believe, yep, under 2500 right here. Air's Reynolds number is about 1600, so that's within our range there. So air works perfectly fine for what we're doing here. We do want to have our viscosity number written down, which I do have that already. And that'll help us out later on with some of the theory stuff and some of the calculations. So we can go ahead and click close on there. And then a couple little more housekeeping things here. We want to get our inlet velocity and our boundary conditions here. So you can go ahead and go to that. For our inlet velocity, we're given 5 meters per second. Click apply and go ahead and close that. For our wall, the lower wall, we want to click moving wall here. It's going to be absolute velocity, and it's going to be 2 meters per second in the negative direction. So you can go ahead and click -1 here in the X, and go ahead and click apply, and then we can close that. We can go to upper, pull that up, do the same thing, moving wall, absolute. We're given 3 meters per second for the upper wall. You can go ahead and click apply and close. And that should do it for our boundary conditions. Next, we want to initialize all this, so you can double click initialize down here, hybrid initialization, and click initialize. You should see it should go through here. Yep, initialization is done. Then we can go to run calculations. So you can go ahead and double click there. We're going to do 200 iterations, just so we have enough points, and you should be able to click calculate here. You should see it start to go, yep, right here through the iterations. And that's looking right so far. And then once that's complete here in a second. Yep, calculation's done. All right, perfect. So now we can go ahead and begin working on our contours. So for our first part here, we're doing velocity contours with vectors. So to do so, we'll go ahead and down here to graphics. We'll go ahead and double click on contours. We'll set that to velocity, velocity magnitude, and select all of those points there. Hit save and display. Yep, should get something looking like this. That's exactly what we want. As you can see already, you have a little boundary condition right here and up here. But to be more precise, we want to add vectors to this. So to do so, we can go ahead and close here. Go down to vectors. We want velocity, velocity magnitude. Go ahead and select all of those, save and display. Close out of that. And you should be able to zoom in here. And yep, you can see the little lines here. That's going to be our velocity vector there. And you can see all the vectors here, and that's exactly what we want to zoom in on. And then we can go to scene down here, contour 1 and 2, or contour 1 and vector 1, and we can change this number, we'll just say about right there, just to make it a little more transparent for us here. Yeah, there you go. You can see all the vector lines right here for our velocity. And that is perfect. That is exactly what we want. And you can see the boundary condition down here. You can see I'm heading in that negative direction, negative x direction. So yeah. So that'll do for part 1, or part A, sorry. Next, we need to show our pressure contours. So to do so, we'll go back over to contours. Perfect, it's already set up. We want pressure, we want static pressure. And we can go ahead and select all of these. Save and display. You should get something that looks something like this along the flat plate. Then we want dynamic here. Dynamic pressure, save and display. Should get something that looks like this. And then we want total pressure. And you should get something that looks something similar to this. Alright, perfect. Now that we have all the pressures there, we can go ahead and go to part C, which is the velocity profiles at the mid and end section on the pipe. So in order to do so, what we're going to do is go down to plot here. We're going to go to XY plot. To get our midpoint and our endpoint, we're going to create a new surface. It's going to be a line rake. We'll go ahead and call this midpoint. For our x0, since the midpoint of our flat plate, our total length was 450 millimeters. So, and half of that is going to be 0.225 meters for x0 and x1. For y, we want to leave that at 0. And then for y1, it's going to be our height, which is 0.003. You should be able to create that. And then we're going to make another one for our end point. And for our endpoint, this number is going to be 0.450, the entire length of our flat plate. And the y we can leave the same. So go ahead and create that as well. Okay. What we're going to want to do here is change this to 0. Change this, velocity magnitude. We'll go ahead and change that to 1. Then we'll click our midpoint and our endpoint to graph. Is it maximum? No, it's just velocity profile. Okay. Yeah, here we go. There we go. We want it in the y-axis. Okay. And that is in pressure now. Okay, velocity magnitude. Okay, there we go. All right. So you should get something that looks something similar to this. You can see here how the curve goes around. So that's exactly what we want to see right there. And that will do for, I believe, part C, right? Velocity, yep. Okay, so then for part D, what we're going to do is determine the maximum velocity and the height at the maximum velocity using the Fluent result. So in order to do so, we'll go down to here to report. We'll double click surface integral. Here we'll go to vertex maximum. We want the velocity magnitude. Can compute, and here's our max velocity at 7.319. And to find that, find the height of that, we can go along this curve here, 7.3, right about here, to get our height, which is 1.70 times 10 to the negative 3 for our max velocity and our max height right there. Okay, so that is part D shown. Now we can go ahead and get to part E, which is with some of the theory. So in order to do so, I'm going to switch over to my Word document here, which should have some of the theory written out here. Alright, so for the theoretical pressure gradient, what we're going to do is begin with Navier-Stokes. We're given that it's steady, it's fully developed, and we want no vertical velocity. So we can go ahead and use this equation right here. To get our velocity profile function, we can perform a double integral with respect to y And you should get a result like this with two constants here. To find our constant values, at y0, our velocity profile is going to be at the bottom velocity, and at yh, it's going to be at the top. So for C2, obviously, if UB is equal to 0, C2 is going to be equal to 0, and C1 you can derive out this equation here. Once you have both of these, you can plug both of them back into this original equation up here, and you should get something like this that becomes the entire velocity profile function. To find the average velocity, you can integrate over the velocity profile, or integrate the velocity profile over height, excuse me. And in doing so, you should get an equation similar to this. And then to solve for our pressure gradient coefficient, what you're going to do is solve for dp over dx, and you should get something similar to this. And then, like I said before, for our viscosity, we wanted to save that number. It's saved right here. For our height, obviously we're given that height. And here are our two, average velocity and the bottom velocity. And in doing so, you can plug all of this into this equation right here and get 107.364 for dp over dx. Now, when comparing it to our Ansys results, what we can do is go to surface integral. Down here, you should be able to go to average weight average. We want pressure, we want static, we want, deselect all those, we want endpoint to midpoint. Nope. Endpoint and midpoint. And you should be able to compute here. Okay, perfect. So in doing so, we're given the static pressures here of our midpoint and our endpoint. And to solve for the dp over dx, it's just going to be simply p2 minus p1 over the length of our plate. So doing so, you should be able to get, should be some number just a little bit over 24 here, divided by our entire length of 450 millimeters. In doing so, you should be able to get a result similar to this. I believe I do have a calculator here. So you should be able to do, like I said, the pressure of our midpoint, which is 24.1019, minus, which is also a negative, of our endpoint of 0.064, and divided by that. And you should get a number around 105, and that should be about right. And if you wanted to find the error, you can do our theoretical minus our Ansys over a theoretical times 100, and you should get something around, I believe it's like 1 to 2% for our error. And yeah, I believe that wraps up project 3. Thank you for listening, and have a good day.